Yes, sir. Proceed, sir.
Yeah. Good afternoon, everyone. I assume that I'm audible. Is it
Yes, sir.
okay?
Yeah, it's audible.
Yes,
It's
sir.
audible.
Yeah. First of all, I would like to thank Vice Principal Dr. Sridhar Garu for inviting me for this session, and also all the other faculty who are involved in organizing this session. Okay. Before going to feature extraction, I just wanted to be very interactive with everyone, but it's not possible. However, uh, I'll try to be more interactive whenever it is possible. Okay. So nowadays we listen the word feature very often. For suppose if we go to purchase a mobile in a mobile store, what we try to do is we will look into the features or specifications of a mobile. What here we are trying really, we are checking like what is the size of mobile, or what is the specifications of front camera, back camera, price, etc. And for suppose if we have two mobiles in our hand, so what will we do? Here we'll compare price of mobile one with price of mobile two, and then size of mobile one with size of two, mobile two, and so on. Finally, we'll make a decision depending on the features they have provided. So finally, what we are trying to do here is we are trying to put all the features in form of a vector, or we are making a decision depending on the features here. Okay. So this is a simple example like how we are using features in everyday life. And I don't know how many of you have seen the movie Khaki. It's a Tamil movie which is dubbed in Telugu, so I assume like everyone have watched this. Okay. So the main plot of this movie is based on a real-time incident which happened in Tamil Nadu. Here the police got fingerprint of a culprit or a dacoit who used to commit murders and uh, theft across Tamil Nadu and Andhra Pradesh. So what happened in this is, here the fingerprint expert used to check or have checked all the fingerprints available in the database manually. And the guy here, he is expert in real life, and he's the one who checked the fingerprints in real life. And if you can see that the image in rightmost corner down, you can see a form of a snake. So this guy is checking for like a snake kind of feature in this fingerprint. Okay. And it almost took years to solve this case. Assume with the current technology, like how much time do we really need to crack this? As simple as this is, just we need to email the fingerprint to the corresponding jails or all over the jails in India, and they have to really just run matching code, matching algorithm to find best match or to find the culprit. As simple as that. It might take hours to solve this case. So basically, what is feature representation or feature extraction? Here we try to represent the discriminative information of a image or signal in form of a feature vector, which in which the size will be far less than the previous case. So here I'm taking two signals and have extracted some vectors from these two signals. So for suppose, let us assume the same case. Here we have like a fingerprint database, which we have taken from a jail or from some other place. So here what I try to do is I will try to somehow extract features from each of this fingerprint. And then I have like a query on right hand side. So I will take a vector or feature vector from this query vector as well. Here what I try to do is we'll compare with each and every vector present here. So here we have like some n number. So here first we'll compare this vector with first vector and second with second vector and so on. For suppose if we have two points in space which are very close to each other, so the easiest way to find the distance is finding Euclidean distance. For suppose if the 2 points are same, or if we get queries and the sample in the database from the same guy, ideally the distance between two vectors should be 0, or else we can simply say that if we get a minimum in the database, or if you get very less score when you compare two vectors, then we will directly match to that fingerprint. This is as simple as that. So this is an example which I am explaining. So, and here, like, while we are analyzing the performance, we have like something called false positives, which means we'll match an innocent people to the culprit in the database, and there is false negative as well. Really, we have some culprit in the database, but our algorithm is unable to detect that culprit, and also accuracy, like how many uh, images has matched accurately. These are the performance measures that we generally look here. So there is one more example. Before going to feature extraction, I just wanted to give a problem. For suppose if we are given with a problem, and there are like some group of students, we know only the names and no information is given, and if we are asked to classify them into high school students and preschool students, can we make that? Probably no. If we don't have information other than names, because name can be anything, so we can not simply do that. Then for suppose if they give us heights along with this names, probably we can do that, because with the age, height will also get increased. In that case, somewhat we can do that. So the simplest thing I can do is I will try to project this data in one-dimensional space. So obviously one dimension is not available, so I have projected it two-dimensional. So I have like different data projected here. So I have like two clusters separated, okay, and I have like two boundary points here, which I have circled it. We can observe that. So the easiest way is we can make a threshold depending on here somewhere around 85, and here it is 60. So 60 plus 85 by 2, we'll get a threshold here. And if you give some height of a new person, for suppose if it is 100, so we'll put it on the right side cluster, so we can simply say like he is high school student. And the other side, if we get like something which is less than 70 or something like that, so we'll put it on the left side, so we can classify it as preschool student. Okay, we'll get into one more example. So here I have given like two variables. One is height and the other one is weight. So if I project this into two-dimensional space, I have like cluster and one more thing. So in the previous case, what happened? Because we have only one feature, simply it became a threshold. Okay, and the next case, what I'm having is a two-dimensional one. So here I have a line which is separating the two clusters. For suppose if I give one more variable, so simply this becomes a three-dimensional vector space. And instead of a line separating these two clusters, we will have some plane separating the clusters, which is the basis of like support vector machines. In the previous case, what we have checked here, if we observe, like we have taken two closest points for finding the threshold. And in case of support vector machines, what we'll do is we'll take the features which are uh, very close, uh, which are lying on the boundary of class C1 and class C2, so which will form like support vectors, and we'll try to find the best margin. This is how support vector machine works. Okay. And first of all, like before going to signal feature extraction, we'll have a brief overview of signal classification approach. So here we'll have signal acquisition, then it can be image or signal. Again, in image it can be face, finger, or palm, or any histopathological image or biomedical images. And in signals it can be speech, ECG, EEG, or EMG, or any kind of signal. And then feature representation, and then again, in order to classify that, we'll use a classifier. So hereafter I will focus mainly on feature representation. Whenever once we get the feature representation, then the only thing we need to do is we need to give it to a classifier whether it is supervised or unsupervised. If it is supervised, it is like support vector machine or nearest neighbor classifier, or unsupervised, it is like clustering techniques. And overview of my uh, presentation is, first of all, I'll give some applications in real time where we use this feature extraction, and then overview of feature extractions, and then feature extraction in signals. So my, my main research interest is in signals, so I'll focus more on signals, and then feature extractions in images with applications in face and this fingerprint, and then dimensional detection with MATLAB exercise. So first of all, applications, authentication systems. So generally nowadays we are using smartphones, and if we use some code or some pattern, it is very easy for other persons to break it. But if we use some biometrics like fingerprint or face or something like that, it is somewhat secure. Nowadays, every electronic appliance, they are coming with authentication things like fingerprint or face or some other things. And also even some nuclear power plants and these kind of things, they need high threshold for authentication, and for household purposes, something like mobiles or something like that, we need less threshold. In the previous session we have seen the scores. So for highly secured thing, we need less score or high threshold, and for less secured or like something like mobile or home appliances, we need less threshold or high score. And then again, security, home surveillances and everything, forensics, as we discussed, like fingerprint example in the previous slide, and medical diagnostics. For suppose if we look into this epilepsy detection or cancer detection or diagnosis of cancer, and everywhere we use this, and even in health industry. For suppose like now there are like many medical uh, medical devices where we can make automatic decision. There are something like artificial pancreas or some other things, and again driverless cars, which is uh, very attractive field nowadays. And fault diagnosis, it's mainly for mechanical engineers, fault diagnosis in gears or other things, and also in finance. Even in finance, we use feature extraction techniques. And before going to feature extraction, I wanted to discuss one more thing: information fusion. Why it is very important to know information fusion is, sometimes it's very easy for us to fake a fingerprint. For suppose if we have a terrorist or some other one, and if we have like multiple sources, we have to use all the sources to make a decision. So mainly used information fusion techniques here are voting. So if we have like four sources, information sources, I will match fingerprint with fingerprint. Again, we have to match apples with apples. Apples should not be matched with oranges. So I will match fingerprint with fingerprint, and then it will make a decision whether it belongs to a person or it doesn't belongs to a person A for us, for suppose. And again, we'll match face with face, and we'll make a decision palm with palm, and again voice with voice, we'll make a decision. So here we have like four decisions, and depending on the majority, like if three of these decisions say like, yeah, this guy is person A, then we'll decide that this person is person A. And like feature level fusion, what we'll do here is, we'll take features individually from each of these sources, and then we'll simply concatenate these vectors, and we'll get a final feature vector. Before concatenating, we'll normalize it as well, because these will create some non-linearities as well. And again, there is something called score level fusion. So in this case, what we'll do is, in the previous case, we have seen like how fingerprints are matched using Euclidean distance. So we'll we'll compute Euclidean distance with each of this source, And finally, at the end, instead of making decision depending on least score, we'll merge all the scores or we'll sum all the scores. And even multiplication is also one way of information fusion. We can either multiply the scores or add the scores, and we can make a final decision depending on the consolidated score. Yeah. And signal feature representation. Mhm. So like in case of physiological signals, EEG signal representation is used for diagnosis of neurological disorders, including epilepsy and like mental health, etc. In case of ECG, we can it is used for diagnosis of cardiac arrhythmias and also obstructive sleep apnea and many other applications. And EMG is used for like diagnosis of neuromuscular diseases. And in speech, we have like plenty of applications. Feature representation of speech is used for classification of voiced and non-voiced, and gender recognition from speech, and emotion classification of speech, and also speaker identification, speech recognition, and everything. There are many applications in speech, especially. Well, depending on the technique what we are using. So simply, if we get a data, we generally don't extract feature directly from the data. First of all, we'll do some pre-processing. It's generally like noise removal or some other kind of things. And also we'll try to decompose the signal, because most of the times the data what we get is highly non-stationary in nature. So first of all, we have to make it as stationary as possible, or we just wanted to make it a narrow band signals. So we go for like time frequency domain or frequency domain features as well. Best example for time domain features are mean, variance, and entropy. These kind of features computed from the signal itself. And frequency domain features like signal strength and PSD, power spectral density, and these kind of features extracted from frequency domain. And time frequency features are something like Mel frequency substitution coefficients, which we generally use in speech, and like short time Fourier transform based, etc. Mostly nowadays people often go for like time frequency or frequency based, because time domain in time domain mostly this frequency information is missing. So depending on the application, again we'll choose the pre-processing or like pre-processing thing. Well, this is an overview. Like we don't have a single medicine which is suitable for every disease. Here we don't have like a single feature extraction technique which is suitable for every signal. So suppose if we go for EEG signal analysis, like PCA, they have used very extensively, and time frequency based features, including discrete wavelet transform, Gabor filter, and empirical mode decomposition based features are also used in EEG signals. When it comes to ECG signals, ECG parameters, something like QT or RR interval, which we'll discuss later, and tunable Q wavelet transform and Gabor filter based features are extensively used in this domain. Coming to speech, they use like zero crossing rate, and in frequency domain features like fundamental frequency, and time domain frequency and time frequency features like Mel frequency substitution coefficients and Gabor filter features have been extensively used. So before going to feature extraction, I'll just give an overview. So Fourier transform, I feel like every one of you know Fourier transform, so I'm not going deep into this. But the disadvantage of Fourier transform is it doesn't provide any information for time localization. This is the main disadvantage, and this is the reason why we often go for time frequency domain based features. And we have an example here. For suppose this is a stationary signal, like the frequencies remains same throughout the signal, and there is a bottom, there is one more signal here which is non-stationary signal, and here we have the same three frequencies which are present in the above stationary signal, but here the signal we kept it at non-stationary nature. I mean, like at each time interval, like we have like different frequencies. When you compute frequency Fourier transform, you can clearly observe Skypes with no side lobes in case of stationary signal, but in case of non-stationary signal, there are some side lobes. Even this Fourier transform is not recommendable for non-stationary signal analysis. But however, in real time, whatever the signals we get, for suppose speech, which is always corrupted with noise, and speech signals itself is like non-stationary, and EEG signal, ECG, every signal is non-stationary in nature. That's why the reason we go for less frequency domain based features. Next, DWT, so discrete wavelet transform. Here what we try to do is we'll try to separate high frequency components and low frequency components by passing through a filter bank. So we have like G of n high pass filter and H of n low pass filter. So we'll get like approximation coefficients, which is like low pass approximation of the signal by the end of low pass filter, and we'll get high pass signal, or on this one detailed coefficients when we process this through high pass filter. So finally, at the end, what we try to do is we'll get like different coefficients, but again the length of vector will be very large. So what we can do, what we will do here is we will try to extract features after processing it through DWT. And the disadvantage of DWT is, for suppose we can see here, we'll get the frequencies from 0 to pi by 2 by the end of low pass filter, and here we'll get pi by 2 to pi hertz. And here I forgot to mention one thing: cutoff frequency of H of n is pi by 4 low pass filter, and high pass filter like we'll have pi by 4 as lower cutoff frequency. So by the end, what we'll try to do is we will try to take some wavelet energy or wavelet entropy or some features, instead of taking all coefficients or instead of using all features at a time, because the more the features will not always give us the best performance. Because of that reason, we will always try to take best features of that. And the disadvantage here is here we are able to extract signals based on predefined filter banks, so we don't have like adaptive filters here. So for this reason, there is something called empirical mode decomposition here. Like we will try to decompose the signal into narrowband signals. We will try to make it narrowband instead of taking non-stationary signal. For suppose here there is x of t, so here we'll decompose x of t into summation of IMFs and then a residue. So the conditions for computing IMF here, like there are two conditions, we'll come to that later. So number of extreme and number of zero crossing must be same, or must be differ, or differ at most by one. See, first of all, I'm taking a non-stationary signal here. What we need to do is we need to compute local maxima and local minima, and we have to join all the local maximas as shown here, and we'll get one more local minima, and then again we'll compute the mean, okay, mean of those values, and we'll get one more signal. And after that we'll go for step 2, h of t is equal to x of t minus mn of t. If this h of t satisfies these two conditions, like the number of like zero crossings must be same or differ by one, and the second condition, the mean value of envelope defined by local minima and local minima is 0. If we have these two conditions, we'll get high MF, or otherwise we'll follow these steps 5 and 6 until we get a residue. So here is an example. I am taking a non-stationary signal. Okay, so I'll try. So by the end, it will give me some first IMF and second IMF. So I will decompose this signal into IMFs. And there is something called Gabor filter, because the complexity of empirical mode decomposition is very high. So because of that, people often go for Gabor filter, which is nothing but product of exponential function, which is a product of complex exponential function and Gaussian function. Uh, we all know that Fourier transform of Gaussian function is a Gaussian function, and when you are multiplying in time domain, this turns out to be a convolution in frequency domain. So when you multiply a complex exponential and Gaussian in time domain, it's nothing but convolution of complex exponential and uh, Gaussian in frequency domain. So again, in frequency domain, representation of sinusoidal signal or complex exponential is an impulse function, and when you convolve Gaussian with impulse, you will get a Gaussian itself. But there will be a shift because of this multiplication, or simply this is nothing but a modulation. In simple terms, you can assume like modulation of a Gaussian pulse. So depending on this center frequency f, we will get different band pass filters. For suppose if you make this fs0, this is a simple Gaussian function or a low pass filter. And as I said, like we can directly extract features from the signal, or we can decompose the signal into some mm, some narrowband signals, and then we can take some statistical features from each of this signal. And there is one more way of feature representation, which are like recently proposed, which are nothing but local descriptors. If we take statistical mean or statistical variance or entropy, they are very good measures. However, like they will compute taking that entire signal into a single window, or like we will segment the signals into windows as shown here. Like what we do is normally we'll take entire signal as a window, and then we will compute statistical mean or variance or something like that. Or we can make we'll generally make small windows and then we'll make. But there is something called local descriptors, which are recently proposed by a group in UK. So what they will do is they will analyze the signals in smaller windows. As I said, like most of the signals, they are non-stationary in nature. It's very important for us to analyze dividing this signal into short windows. So here we have like something called local descriptors. So I'm what we do is here we have a sequence. So we'll leave first 4 samples and we'll start from 5th sample. So here I'm having 25. So 25 is compared with 28, and again all the neighboring samples. Since 28 is more than 25, we'll get 1, and 15 is less than 25, we'll get 0, and finally we'll make a string, binary string here, and we'll compute a decimal value. Okay, for each of the point in signal, we'll get one LBP code. Finally, we use distribution or simple histogram taken from the signal as a feature vector. So, and I'm going to show one application, so which is recently proposed by me. So, obstructive sleep apnea detection using singly DC signals. So the motive for choosing this is this mainly affects middle-aged people and characterized by repetitive airway obstructive blockage, and this is main reason for cardiovascular system as well, cardiovascular system failure as well. Generally, PSG signals are used, and alternatively ECG signals are used, because like ECG is very simple to load. So I have taken like publicly available database here, which is taken from 35%. And here the evaluation metrics are somewhat different from the previous like false acceptance rate and false acceptance rate, what I have discussed previously. Since COVID is the disease which is affecting here, so instead of taking obstructive sleep apnea, we can put a COVID here. So true positives, you can say like uh, COVID we have identified correctly, and true negatives, normal cases identified correctly, and false positives, normal signals identified incorrectly, and false negatives like COVID negatives or like COVID negatives, COVID signals are identified incorrectly. Why I'm telling this is it's very important to know about specificity and sensitivity along with accuracy. For suppose if I'm having uh, a test data set with 100 normal cases and one COVID case, and if I if I correctly classify this 99 normal cases perfectly, and this COVID case is kept it in normal case falsely. So in this case, we'll get accuracy as 99%. However, like we'll get zero sensitivity. So it's very important for us to look into specificity and sensitivity, like how we looked into false acceptance and false rejection rate. So this is the approach proposed by me. So we have ECG signal, and then I have decomposed it using Gabor filter. Again, I have taken histograms after computing phase and magnitude. And again, here comes information fusion. Since we have like three narrowband signals, I have received like three vectors. Simply, I have concatenated this histogram, and then I have given it to least square support vector machines. And here one important question is like, how will we choose the parameters? The simple logic is we should not lose any information, so we have to keep information as much as possible. uh, in my case, sampling frequency is 100, so we need all the frequencies from 0 to fs by 2, which is 50. So I have designed my filter such that I'll cover all the frequencies over there. So this is how like I used that phase information. Since I get a complex number for each and every response, because Gabor function is a complex function, and when I convert my signal with Gabor function, I will get a complex number. So I used phase taken from this this Gabor output as feature. So, and I computed like 1D local pattern, which is equivalent to 1D local binary pattern. And again, I have thresholded. So I got 1D local pattern as well. And here we have, in the previous case, I took like Gabor filter based features. And in general, like the basic parameters we use for EC signal is we generally go for this ECG parameters, RR interval. So this wave is generated due to the electrical activity of heart. So we generally take RR interval and this QTC, and here there is T wave, and here is Q and QT, and also heart rate and PT, and these kind of features are generally used to represent these ECG parameters, but these are not very effective. That's the reason like most of the people, they go for tunable Q wavelet transform based features. These are also very effective for classification of ECG signals or ECG based events. So yeah, next comes speech classification. So the often we go for zero crossing rate when we need to classify voice and non-voice signals. So non-voice is mostly like noise kind of signal, so which is corrupted with noise and everything. So it, we'll compute zero crossing rates of non-voice and voice signals. Generally, zero crossing rate is more for non-voice. So if we have like more zero crossing rate, we'll put it in non-voice category, or if it is less, we'll put it in voice category. This zero crossing rate is mainly used, this voice non-voice classification is mainly used to extract speech or voice spot from speech signal. So by eliminating this non-voice spot, because whenever you wanted to use it for speech recognition or something like that, so we don't need that non-voice spot. We mainly depend on voice spot. So here we use zero crossing rate. It is very simple, like in a given duration of speech signal, we have to count the number of zero crossings, okay, or number of sign changes. Simply we can measure the sign changes in a signal. And then comes substrum or capstrum, which is nothing but spectrum of spectrum. Here we have like inverse Fourier transform of log of Fourier transform of some signal x of t. Okay, so here x of t is my speech signal. When you apply Fourier transform, we will get spectrum, and when we apply logarithmic of this Fourier transform, then we will get this log spectrum. And again, when we apply this inverse Fourier transform, then this becomes substrum. And again, we are back to time domain, because when we apply Fourier transform, we move to Fourier domain, and when you apply Fourier F inverse, then we are back to this time domain. Let's see why we compute this substrum, or like why is very important to learn this. So here I have a speech signal which is in the leftmost corner. Okay, when I applied DFT, I didn't get the information about the dominant frequencies in this signal. But again, once when I apply this logarithmic, so I have some information, but again, I don't have like very much good information about this dominant frequencies. And however, I am having some harmonics as well here. So once I compute IDFT, you can check this harmonic here, which is very clearly visible. And so why is this? Why we are going for this? This is like vocal fold vibration. So whenever we speak, there is some glottal pulses, and this will be released from our vocal tract, and we'll get speech signal as output. So, and we are mostly interested in getting this vocal tract information, because this is different for different people, and we can model this speech signal as vocal tract convolution with glottal pulses, because this vocal tract here will act as a filter. Okay, so when we go for frequency domain, which is nothing but x of t becomes x of t is equal to e of t convolution with vocal tract convolution with glottal pulses. So in frequency domain, this becomes just a multiplication, and when you take logarithm, then this becomes addition. So when you compute IDFT, here we get both vocal tract and vocal and this glottal pulses as well, but we are mainly interested in this part. Because of this, we generally go for mel frequency substitution coefficients. The idea behind going to mel frequency substitution coefficients is like human ears are very good at recognizing a person depending on speech or something like that. Depending on human perception, they have designed this mel frequency band. Okay, so here the steps are same as the previous. The only difference is here, after computing F50, we'll go for mel filter banks, and we'll find the response of mel filter banks, and then again we'll compute log filter bank energies, and then again, instead of inverse FFT, we just go for DCT, because we'll get the advantage of using DCT is we'll leave that phase information, and we'll keep only this frequency information. And here we have like 13 filters, so we'll get like 13 coefficients. However, like the first coefficient will have like some DC components, so mostly we'll use for like 2 to 13 things. So this is the equivalent as well. and like there are other versions, um, LFCCs and Rasta, and also, so please go through that as well. So I gave only the basic version of Mel frequency substitute coefficients. And the next one is face recognition. So in face recognition, the basic steps what are involved is, uh, first of all, we'll have an image or video, and then we have to detect face from that uh, image, depending on some color or some other template, and then again we'll take this feature and we'll identify depending on this. So coming to face recognition, generally people go for, you know, uh, generally people go for some identify some areas in face, and something like iris or nose or mouth, and then instead of taking all the face, we will take this and we'll match to the corresponding face in the training set. So this is easy because uh, this nose width and these variables, they don't change a lot, and very hard because it's very difficult to detect these features perfectly. Okay, and instead of taking features, geometric features from this face, like size of the face, or like width or height, we generally go for generalized feature representation of face or images. So again, most extensively used features in face recognition is local binary pattern. Here what will we do is, we will take a center pixel, sorry, we take, matrix, because an image is nothing but a matrix. So we'll take a 3 by 3 matrix here, from the face, and then we compute local binary pattern. So here the center pixel value is 92. So 92 is compared with the all the other samples here. So here what we are comparing is 92. We take this 92 value and then we try to compare with the neighboring values. So just look at here. So here 92 is less than 94, so we'll replace it 1, and then again 90, it is less, so 0, 88, 0, so on. We'll compare with all the neighboring pixels and we'll generate a binary number, and we'll replace this point with this decimal representation. Similarly, we will compute LBP for each and every pixel available here, and finally we'll take distribution as a feature vector. And there is something called multi-resolution LBP as well. Instead of taking 3 by 3 neighborhood, we will take like 5 by 5 or some other neighborhood, and with different resolutions. So one time I can take 3 by 3 and next time I can take 5 by 5. So I can combine the two vectors and I can make a somewhat a larger vector, which is having like multi resolutions here. So we have like multi-resolution, multi-resolution representation of face using this LBP as well. And PCA is also like the most oftenly used uh, feature extraction technique. So we'll go for a MATLAB session here. So any questions up to now? So yes. Hello. Hello.
Sir, yes, sir. Yes, sir.
Yeah, yeah. Hello.
There are no questions till now, sir.
No, but there is someone who raised his hand actually.
Sir, let me check, sir.
Kyati Srivastava, something like that.
No questions, sir.
Okay. So here I'm taking a case of simply classifying a given EEG signal, whether the person has, hello? Yeah, whether the person has been anesthesia or simply is active. So we all know that like in EEG we'll have like alpha, beta, gamma. So if a person is active, then he will be having some EEG activity. As a result, there will be some high power, high power in or like high power associated with that. Okay, here simply what I'll do is I will compute power spectral features and try to decide whether this is anesthesia or uh, simply he's active. So I'm trying here. So here I'm using like different filters in order to get like different outputs. Okay, so here like delta power, theta power, and alpha power. So what I did here is I just computed frequency response of each of the filter, and then again I have set some threshold here. So if the average value is greater than some value, and again like we'll have like four alpha, theta, beta, and gamma. So if these four activities are some greater than some threshold, then I'll put it as wake or active case. And for suppose if it is less than some threshold, then that means like that person is having less brain activity. As a result, the EEG will have less power, and I'll keep it in anesthetized kind of thing. And this is one case. And again, so is my MATLAB editor available for you? Is it visible? Hello?
Sir, sir.
Is my MATLAB editor is visible for you?
No, sir. Only people.
I have showed you some program. Is it visible now or not?
No, sir.
No?
Not visible, sir.
Okay, okay. 1 second. I think I have to. So how to go to home? Any suggestions?
Sir, close this window and again share the screen, sir. MATLAB.
Okay. Yeah.
Now it is visible, sir.
So I'm sharing my MATLAB screen. So this program seems to be very long, but there is nothing very complex here. Simply what I try to do is we have like 4 bands: alpha, theta, beta, and gamma EEG bands here. So depending on the like higher and cutoff, lower cutoff frequencies of this alpha, beta, gamma. So I will compute filter response, and finally power spectral density I'll compute by the end. So if the power is less, what does it says is the person is anesthesia, or like he is given some anesthesia. And if the power is more, what does this mean? It mean like this guy is active. So this is the basic kind of thing. So here I am taking like power spectral features. So I'm running this code. So so these are the averages or power averages from the 4 spectrums. So and it is, I have a simple logic, rule based logic, or I'm not using any classifiers here, nearest neighbor or SVM. So what I'm trying to do is I'm checking like whether the power is greater than some threshold in all the cases, because I have like 4 bands. So I check in each of these band. For suppose in first band, if it is greater than 41, and in second band if it is greater than some 0.57, and third band if it is greater than like 0.27 and 1.89. So this means like this person is awake, and if it is less than, then there is less brain activity. So in this case, the person is anesthetized. The sample which I have taken here is having all the values less than the thresholds. So the logic is very simple. I have classified it using that. And next, I'm going to my presentation again. Sorry, it takes some time to close my MATLAB. It's slow. Yeah. Sorry. Again, when compared to face recognition, fingerprint formation is something, fingerprint recognition is something complex. Here, generally, we don't directly compute features from this. First of all, we'll try to extract some features within the fingerprint. Because fingerprints are having some special properties. Generally, these are unrelated with any other person. For suppose if face, we can have some uh, similarity with some other guy, but these fingerprints really they are very unrelated with other persons, except in case of identical twins, they'll have like some generic similarity. Otherwise, even parents and childs also, they are not very similar. And in case of fingerprint, we have to look into these features which are given over there: core, bifurcation, ridge ending, and all these kind of things. In the first slide which I have shown, simply the person is looking for like a snake like structure inside the finger. Similarly, we'll have like these are the some of the features that can be extracted. So bifurcation, it's the intersection between two lines which converge or diverge. And arch, they're found in most of the patterns. It's like you'll have like arch kind of pattern. And loop, we'll have a recursive line which leaves from this same side of fingerprint. And again island, between two lines you will have like one line which is not ending, simply like an island. And ellipse, sorry, and this tented arch. And these are some of the features which are available here. Okay. And how is it different from the normal kind of thing? So in fingerprint, in normal face recognition, we have seen like how we have extracted directly this LBP or some other patterns. But in case of fingerprints, we often take features first. For suppose we can take some pores which are we can detect pores which are available in the lines. If you see like these are the sweat pores, and these are very different for each of the person. So first of all, we have to detect these using some filter masks and everything. And the most commonly used filters here is again Gabor filters. Also Gabor filters are very often used, because they have like direction as well. In one dimension, we generally leave direction theta, because in signals we generally don't have any theta. But in two-dimensional Gabor filter, what we'll have is we'll have two exponential terms, and again two um, again two inclination, or what you say, angle as well. So here, by adjusting that, we can simply detect this, and we have to match by replacing one over other, and we'll match this fingerprint. So before going to dimensionality rejection, we'll go for one example in fingerprint as well. Mm, 1 second. I'm sharing my MATLAB. 1 second again.
Sir, your voice is not audible, sir.
No, no, I'm not speaking anything. I'm just changing my window to MATLAB.
Okay.
1 second. Sorry, invest room. Hmm. Any questions meanwhile? So I think it is taking some time. Yeah, I'm ready with this. Well, I'm sharing the screen. So here an example for like feature extraction in fingerprints. So here it's not completely visible. Here you can see only the matching part. So what I'm trying to do is I'm detecting the lines on the finger, and directly I'll match the lines using those fingerprints. So it seems like it is taking some time. Probably I will skip this and I will come to dimensional detection. We will check this in the end. Oh. Oh. So I'm starting dimensionality reduction, and so there is one logic. So increase in number of features will always not give us, the better accuracy. And in practice, inclusion of more features, like some irrelevant features, will degrade the performance. So we have to somehow reduce the dimensionality and put meaningful information together. So the main objective here is, we have to choose, like, optimal dimension without compromising the performance of our system. So here there is one graph where, like, performance is increasing to some extent with dimensionality, and at some point, even though we increase the number of features, the performance is reducing. So we have to use the optimal number of features in order to get some good performance. So here, like, we have two kind of thing, like, one is directly feature extraction. So even, like, this we also called as a feature extraction, because this can be used for as a features as well. And the other one is feature selection process as well. So we'll have a set of features. Just a minute. uh, Here we have some features, feature matrix x1, and we'll transform it into some f of x. We'll use some f of x, and we'll get some y, where the dimension k is much lesser than the existing, is less than the existing dimension. And there is something called feature selection. Here what we generally do is we'll select, the high performing features using some feature selection methods. And here the mapping can be linear or non-linear. Here it's mostly non-linear. So the simple example for feature selection is, we'll compute the mean of features, and we will compute variance of each feature with respect to the mean. And if the variance is high, it means, like, this feature is having good discriminative capability. So depending on the variance, we will rank the features, and we will select, like, top few features in case of feature selection. Here in dimensionality reduction, we'll use some transformation kind of thing. Generally we use linear transformation because it's very simple and also analytically tractable. So here we have some matrix x. Simply we'll multiply with some one more matrix u in order to get y. Or it's nothing but sorry, it's nothing but we are trying to project high dimensional data into low dimension. And if our main goal is without losing information, so here we'll try to keep the data as accurately as possible. If our goal is zero information loss or no information loss, and if our goal is to increase discriminative information, then here in this case we can leave some information, but we have to capture the discriminate information. The best example for this is LDA, and for the other for in zero or no information losses, PCA. And commonly used linear feature extraction methods, or PCA, which preserves the data, and linear discriminant analysis, which will best discriminate the data. And there are some other methods as well, independent component analysis. So what is the main principle of PCA is, we will project the data onto eigenvectors, and we will select the data corresponding to the eigenvectors of highest magnitude. So before going to PCA, we'll see some matrix transformations. for suppose I have a matrix A, which is 1 plus del 0 and 0 and 1. Here each column is a vector. I am considering each column as a vector, and if I multiply this vector with one more vector, simply with x is equal to 1 comma 1. So what happens here is this will have a movement in direction x. So here you can observe, if I take a vector 1 comma 1 here, this will have a movement in x direction, and there won't be any movement in y direction. It can be clearly visible. Just take in matrix 1 comma 1 and multiply with a. So the output is 1 plus del and 1, a column matrix of 1 plus del and 1. Sorry. So here, so from 1 this will move to 1 plus del, assuming that del is greater than 0. Okay, and similarly from here it will move to the other direction. However, if you observe the points on y-axis, which is nothing but 0 comma 1, these will not have any movement. You multiply this with x is equal to 0 1, we'll get the output is also as 0 1. And we have one more matrix on right hand side. So we'll have what we have here is, so what is their question? Is there any question here? Hello?
No, sir. This is poll question for attendees to get the attention.
Okay, fine. Sorry. So here we have one more matrix. Here I am having 1 minus delta and 1 plus del. So what here it will do is, in y direction it will expand, and in x direction it will move towards the x-axis, because here we are using 1 minus del. Because of this reason, this vector expands in y direction, and in x direction it will move towards, it will have a lesser value. Okay. And there are certainly some elements which doesn't move, especially the movement, the elements on the axis. So they are not moving in this case. Okay, so let us take some diagonal matrix here. So I am having lambda 1 0 and 0 and lambda 2, and if I multiply with 1 comma 0, what is the output? So I'll get lambda 1 into 1 comma 0. Here what is happening is, so this is a point on 1 comma 0 is a point on x-axis. So here we are not changing the axis, but this vector is moving along the x direction. If you check this point, this is moving along the x direction. And similarly, this is 0 comma 1. Even this direction, this is moving along the y direction. Simply we are scaling this vectors. So can I write this equation in form of diagonal matrix into unit vector is equal to lambda 1 and e1, which is nothing but eigenvector representation. So this is a simple version. So whenever we multiply a diagonal matrix with only half diagonal matrix with other elements as 0, then we'll simply get lambda 1 times of this e1, which is nothing but we are scaling the vectors. And we can simply conclude by saying that diagonal matrices have the property that they map any vector parallel to standard bias vector. In our case, it's like x-axis and y-axis, which are parallel to x and y vectors. These vectors will map into another standard basis vectors. That's it. And any vector v bar that is mapped into A with parallel axis lambda v is called an eigenvector, and the scale factor will be eigenvalue of the vector v bar. So these observations we can make from this thing. And there is some more special matrix here. This is called rotation matrix. So in this case, especially here if you observe, the angle is 45 degrees. In this case, what happens is the vectors which are at an angle of 45 degrees will are scaled along the same direction. You can observe here. So if we have a vector like 1 comma 1 or 1 comma minus 1, these vectors will have like movement here. So these are like special directions of rotation matrix, and these are some mathematics where if we take that a into x, we can put that a in form of multiplication with phi and diagonal matrix and this. So finally we will end up with a1 is equal to lambda 1, or which are nothing but these elements, diagonals of diagonal matrix, and eigenvectors are corresponding to phi into e1. We'll look more closely here. So here I'm having a matrix, rotation matrix phi of 45 degrees. When I multiply this with 1 comma 0, my output is 1 by 2, 1 by root 2, and 1 comma 1. So what is this here? So is it the first column? And similarly, when I multiply with 0 comma 1, I'll get 1 by root 2 comma minus 1 by comma minus 1 and 1, a column vector. So this is nothing but these are nothing but eigenvectors, are just columns of phi. So if you observe this, these are nothing but just columns of the rotation matrix. So this we are like we'll use this. In summary, like if we have a symmetric matrix, we can decompose that into phi diagonal matrix into phi transpose, and where the columns of diagonal matrix, the columns of phi becomes eigenvectors, and also the elements in diagonal matrix will become simply our eigenvalues. Okay, and we have like one more version. For suppose if we are given with a uh, distribution, and if we wanted to fit a Gaussian distribution using that, so what will be the best fit? The simplest version is we can compute mu, which is mean value, and also the variance, and the best fit will be 1 by root 2 pi sigma square e power minus x minus mu square by 2 sigma square, which is a normal Gaussian distribution. So, and most interesting thing here is the mean squared error is very less when you use these parameters, because in general, while we denote Gaussian, we use only these two variables, mean and variance. So if you compute from our mean and variance from our data, we can simply use it for fitting Gaussian curve along our distribution. And here we have like multivariate Gaussian distribution. One will have non-isotropic and no correlation. There is no correlation between two distributions. In the previous case, we have only one distribution, and here we are having two distributions. So we don't have any correlation. Here, like non-isotropic and no correlation. And here we have like isotropic and correlation. So in this case, we can see like the data is well distributed. So this and how to represent this Gaussian distribution when we have like multivariates or multivariables. So simply we can represent using this Gaussian. However, our variance and these things, we have to represent it in form of matrices here instead of simply using x and y. So yeah, this is how we generally represent. I am not including mathematics here. And if it is non-isotropic and with correlation, we generally go for covariance matrix. And the most of classification tasks that are involved in day-to-day practices, they will have like no isotropic with correlation, because the data is highly correlated with other classes. Not highly, it will be like correlated with other classes. And the steps involved in PCA is, first of all, in order to compute our covariance matrix, we have to compute the mean and then subtract the mean. and then we can compute the covariance matrix using this phi into phi transpose, and again where phi 1 matrices, and we'll compute eigenvalues, and we'll put it in ascending or descending, sorry, in descending order, and we'll if possible, if we wanted to reduce the dimension, we will select the eigenvalues with more strength or highest value, and then we'll use corresponding eigenvectors to use it as a feature vector. So this is how we'll use. First of all, if we have like n dimension, we'll take only first k terms for approximating this, and we'll have like x minus x into u into this. So I'm taking one example here. So we have a problem here. I'm using this for noise suppression. We have a problem like we have a problem. We have a signal with highly corrupted with noise. So for suppose we take a signal, and we'll have like 100 time points in each of the signal, and 200 different vectors. So what I can do is I can add noise. For suppose if I take an x, a sample x, so I'll add noise 200 times, and I'll make a vector 200 vectors. Okay, so in order to compute PCA, first of all I have to subtract the mean, and then again covariance. So we can yeah, subtract the mean and use the covariance. These are the some MATLAB codes for that. So again we will get eigenvalues and covariance. So here, since the data size is of 100, so how many eigenvectors we'll get? We'll get 100 eigenvectors. Sorry, eigenvalues. And if you check this, when you plot it here, only first two eigenvalues are having like some good magnitude, and rest are all having like very less strength. So simply what we can do is we can take first two, or we can retrieve first two eigenvalues and discard the rest of the eigenvalues, and correspondingly we can use eigenvectors for our signal reconstruction. So since there are only two large eigenvalues, so I have taken these two large eigenvalues, and these are the eigenvectors plot. Okay, and these are just two columns in the F matrix. Here we will get vector F, and we'll get eigenvalues V here. So I have taken only first two vectors here. And for filtering, what I'll do is we'll remove here like all the we'll put all the values to 0, and simply I'll I will reconstruct the signal using this F into this Z filter. So this is the signal what I have received after filtering. So this is very attractive when you compute that. And similarly, the same thing can be used for face recognition as well. So I'm giving you one example as well. 1 second. Oh. This. So once I run the, first I will run the code, then I will explain the code according to this. So here we have taken a test sample and we are looking for this and we got a wrong face here. So I'll run it once again. So we got it right. So again, once again, I'll run it. Yeah, we found it a right match. So what we are doing here is we first of all we load the database and we'll select randomly one image for testing purpose, and rest we'll use it for like training purpose. And again, we'll use we'll take the mean because the first step in computing PCA is take the mean and then subtract it from all the other vectors. And again, what we need to do is we need to compute covariance matrix. Again, we have taken then again eigenvalues. So again, I'm picking the eigenvalues corresponding to this few first 10 eigenvectors. So here after taking first 10 eigenvectors, I'm getting this output whatever it is. So this is how, hello, this is how face recognition is done using this PCA. Done with that, sorry. Yes. Hello. Okay, here I think. Well, I am done with this, and if you have any doubts, please go ahead. And these are my contact details. You can find me in LinkedIn and Facebook as well. So this is my email ID. Yes. Hello.
Yes, sir.
Yes. Hello.
Sir.
Yes, sir.
Sir, once again, sir, I'm checking the question, sir. Virami, something, madam, are you there? You can ask the question, madam. Hello. Abhirami. Sir, Abhirami madam is asking about merger graph and implication table.
Where is that?
Abhirami madam is there. She is asking about merger graph and implication table. How to use them?
No, actually, I am not having idea. Merger graph.
Yeah.
Oh, sorry for this. Actually, I'm not having idea about that. Merger graph. Okay.
Yes, sir.
No,
The
sir.
question is not clear, sir. She gave only hint.
No, I never like. I'm not having idea on this.
Participants, if you have any doubts or any questions, raise your questions. So I think there are one question, sir. Is
Okay, sir.
PSO is effective than PCA in future reduction?
Well, like it always depends on the application itself. As I said, like one approach is good for one application, and even it is very data dependent. All these applications, what I'm saying, for suppose if I take a local binary pattern, it is very effective for some database, and the same is not very effective for the other databases. So it's data dependent on as well as application dependent.
I think there are questions, sir. Thank you, sir. Sridhar sir, is there, sir?
Answer sir. Answer sir.
Sir.
Thank you very much, Dr. Sunil Kumar Garu.
Thank you, sir.
Thank you for enlightening all the participants.
Thank you, sir.
Thank you for sparing your valuable time and to attend this virtual platform and enlighten us. And you already shared your contact details, so
Okay, sir.
the participants may feel free to contact you at any point of time.
Yes, sir.
So, and also we have promised to the participants that we are
Hello.
going to
Hello?
maintain a repository of all the PPTs.
Yeah, sure, sir.
Hello,
I will
sir?
share that with you. I will share that with you. Sure.
If you can share the same, at the end we are going to provide this PPTs as well as any other material relevant to your topic of discussion today, feature
Yes,
extraction
sir.
and simultaneous.
Yes, sir. Yes, sir. Definitely.
Yeah,
Yes, sir.
if you can share any other material, that would be more helpful for the participants, especially researchers who are trying to pursue research in machine learning using different machine learning algorithms and feature extraction, face recognition, whatever might be the techniques, they're using different algorithms. So I request you, sir, if you can share the material and all, any other material other than the PPT, you can share it to the participants. So on behalf of Lenin Institute of Engineering and Technology, thank you, sir, for enlightening us. Thank you very much.
Thank you, sir. Thank you very much. Thank you for giving me the opportunity.
Now I request the participants, if at all you have any queries with regards to today's topics of discussion or those topics we discussed yesterday, you can forward the same to us so that we can establish a communication between the resource persons and among you also. We can forward the same to the resource persons and get them solved at any point of time. From our side, we are going to assure this to you. And with regards to tomorrow's sessions, tomorrow morning, we are having a session that is being dealt by Dr. M. Srinivas. Sir is Assistant Professor, NIT Warangal. And then tomorrow afternoon, we are having Dr. K. Ravi Kumar Jatot. Sir is Associate Professor, Department of VC, NIT Warangal. In fact, Dr. M. Srinivas is going to talk about support vector machines tomorrow. It's a lovely, interesting topic and essential for all of us. And in the afternoon, Dr. Ravi Kumar J is going to address all of us on K-means clustering algorithm. So these are the two topics of discussion tomorrow. So as usual, I request all of you to be more active and alert. And once again, I'm requesting you, those who are having any queries relevant to machine learning, or those who are planning to pursue research work in machine learning or relevant deep learning applications, you can use this platform to get your queries answered at any point of time. Though the lectures are finished, we are here to establish a link, a channel of communication between you and the resource persons. So we can communicate on behalf of you and get your queries resolved. So please feel free at any point of time to get all your doubts and queries clarified. So I thank you one and all for your patient listening. So Nachari sir, shall we wind up the session for today, or are you going to
Yes,
give the
sir.
feedback link now?
Already shared in the chat box, sir. They will fill the feedback. So I will wait
Right.
for 5 minutes and we'll close the session, sir.
Okay. So before that, I just want to inform one important thing to all the participants. It is like as per the AICTE norms, all the participants are supposed to maintain an attendance of 80% as well as 60. They have to secure 60% marks in the end examination, right? And as you, Nanchari sir and the other organizers might have clarified your doubts with regards to this attendance, whatever the poll sessions you're going to answer daily, and whatever feedbacks you're going to provide at the end of each session, at the end of the day, these are going to be counting for your attendance. So please be alert and attentive in replying to the polls. Kindly respond to all the polls. Kindly respond, submit your responses in the feedback forms after every session at the end of the day as well. Thank you. Thank you one and all for your patient listening.
And
So
one more,
Nacharya sir, soon after you're done with, you
sir,
can wind up the session.
sir, one more thing is whoever is joining into the Zoom meeting, they need to rename their name with the registered name.
Oh, great.
We cannot understand who is that person. So if they are not renaming it, their attendance will not be coming under count. So they will lose it.
Right.
So
Right.
all of you
So I
should
guess
rename it.
participants might understood this. Dear participants, I guess you might understood this. We are having, in fact, a practical limitation that most of the participants are logging into the session